All right, so now let's look at some interactions that this visible or near visible light can have with ceramics. All right, so light may interact with a solid or ceramic by transmission. So that's when something basically goes straight through. So that would be a transparent material if the transmission is very high. Um, it can absorb into the material. So certain features can absorb light within them. And so that's not really showed here. And then and so that would so the absorption would obviously uh, reduce the transmission in that case. So any absorption would take away from transmission or reflection, and so that material would optically be different. And we can also have scattering. So the light can interact with features within the ceramic or solid in such a way that they are um, scattered in different directions. So there's different types. Rayleigh scattering here, Raman scattering are different types, but effectively there's it just means that there's some type of change to the wave, either amplitude or phase that's happening with scattering. And reflection or reflected light is also added here, but I didn't separate that out in the different types of interactions because reflection can also be thought of as scattering, just scattering in the exact opposite direction of the incident beam. So basically, reflection is just another type of scattering, and so I didn't separate that out in this case. Okay, so let's look at scattering. So scattering can be either coherent or incoherent. And so this phenomenon comes up quite a bit in other techniques as well, where we have other EM radiation. For example, X-ray diffraction, if you're familiar with Bragg's law and so forth, that is built on a principle of this type of interaction that happens with X-rays. Here we're looking at it for visible light, but the same principles apply. So coherent is when we have these visible waves that are in phase. So that means that the peak and the valley of that sine wave match up with the peak and the valley of other waves. And so they're in phase. And so this means that when we look at something that exhibits this coherent in phase constructive interference, it means that the peaks add. So essentially, if we have the same amplitude for each wave, it's multiplied by the number of waves we have here. So for this example, this is 6 waves, and so the amplitude for this condition would be 6 times the amplitude of one of those waves. The other type of scattering that we can have is incoherent. And as you might imagine, if coherent was in phase, this is going to be out of phase. And instead of constructively interfering, which means the peaks add, here that destructively means that they are going to sort of subtract. So here, all these waves are out of phase, meaning that they're no longer have the peaks and valleys match up with one another. And so if you look at these various waves, you're going to see that on net, they would more or less cancel out or lower the amplitude. And so this, if you look at these 2 waves here, you see that the valley of the one matches up with the peak of the other. That's a case where if you add those 2 together, that nullifies the amplitude. And so on net, the amplitude of these types of combined waves is very small. And so we don't get that additive effect. Okay. I also want to look at a concept known as refraction. And so this is, I think, something that you're aware of either directly or indirectly, but this concept of refraction is basically just an apparent bending of light when it passes through uh, different materials. So in this case, it goes through one material then the other. So we can think about that as an incident ray is moving through vacuum or air in one direction, and then it encounters a solid, and it appears to be refracted or bent by a different angle. And then when it comes out of that solid, it would go back in the same direction as the incident being, because it's that same material, either vacuum or air. We can also think of refraction as, if you think of white light, which consists of all wavelengths of visible light. If you expose that to a prism, which now has two surfaces that are not parallel, then this gives us an apparent bending or separation of light, and that's where you get that rainbow effect, where you can separate white light out into the discrete colors of that wavelength. And so with this, for refraction, we can sort of quantify this apparent bending. And so if we have an angle I, which is the angle between the surface normal of the solid and the incident ray, so I is the angle, and then it changes to R in the solid, we can quantify this principle of refraction by looking at the differences in those angles. And so we do that with this refractive index N, and that's equal to the sine of the incident ray angle over the sine of the refracted, I here is for incident, R here is for refracted. And so this is within the solid, this is within air. And so if you take a look at those relative angles, we can quantify the refraction that occurs when we look at these two different materials. So here's kind of another example of this, this apparent bending. If you look at this picture of a straw that's up here within, just in air, and then down here is within a liquid like water, then the light is going to appear bent when it changes materials. And so that means it changes direction, but also that means that there's a change in velocity and direction for this. So we can also look at the refractive index in terms of that velocity. So if we think about it as the velocity of light within a vacuum, so that's a constant, and then we look at the apparent velocity within the solid, we can also use the refractive index, which looks at this bending or change in velocity, to look at the relative velocities in different materials. So we can think about it in terms of angles, but also that relates to velocities. All right, so let's look at table 16.1 in your textbook, which looks at the refractive indices for various ceramics. And it kind of divides it up by class of materials. So there's halides and sulfides up here, and you can see that they all have refractive indexes, which does not have a unit because it's a ratio. So these are the ones over here, which are fluorides or chlorides or bromides, are all pretty close to 1. Here, this zinc sulfide goes up to 2.2, and then this lead sulfide almost 4. So those are quite high. And then oxides down here have are pretty much from about 1.5 up to about 3. If we look at covalent ceramics, those can be a little higher. And then we have glasses, which are frequently used as optical materials. And you can see, again, close to 1.5 all the way up to 2.5. So now what I want you to do is, again, relate this back to, we can think about this as the relative change in direction, but see if you can come up with, what does this mean about the relative velocities of light in these various materials, assuming that we're all referencing vacuum as the incident material. So see if you can come up with which material you think light travels through the slowest. So pause the video, see if you can kind of scan through this table and tell me which one you think light travels through the slowest. All right, so now let's take a look at which one of these is the slowest. So I'll take you back to the previous slide that looks at the relative velocities. So the velocity of light in a vacuum, that is a constant. And so that's not going to change. And so what is changing though is this velocity in a solid. So since all of these numbers are greater than 1, that should tell us that the velocity is decreasing in these solids. And so the light travels slower in these materials than it does in a vacuum. And the relative distance from 1, right, the higher the number, means the slower that travels. And so basically when we want to find the slowest material, all we're going to do is try to find the biggest number here. So if I kind of scan through these, there's a 1 and 2, but we do have a 3.910. So lead sulfide is a material in which light travels through the slowest of all of the ones on this table. So basically the highest number travels through the slowest. And so I just put this here in the slides just to kind of keep people on their toes. But this means just go back to the answer we just kind of talked about for the answer to that problem. All right. So the last thing I kind of wanted to mention here is, again, we talked about the light travels through the slowest. So that means that higher refractive indexes are light travels through more. But another feature of the high refractive index is that there's a higher percentage of light that is reflected. So if you see the higher number there, that means that more light is reflected relative to transmitted. And so a really good example of this is 2 different types of glass that we saw on the table. So lead silicate and soda lime. So soda lime we've used an example in the lab in this class a lot because it's a very simple, very common glass composition. And so this bottle is composed of soda lime glass, soda for sodium oxide, lime for calcium oxide. So it's basically silicate based glass with sodium and calcium in it. All right, so the refractive index is 1.5, which was relatively low on that list of materials. And so we have a high percentage of light that is transmitted as opposed to reflected. But then if we look at a lead-based glass, then we see here the refractive index is higher, actually a whole percentage, not percentage, a whole number, right? 1.5 versus 2.5, so 1 higher. And so that means that the higher the refractive index, we have a higher percentage of reflected glass. And so this is what gives us kind of that sparkle in lead-based glasses. So if you think of like kind of fancy glass, this is, you can kind of see in certain cases it gives it more sparkle, but more reflective. So it's going to look more mirror-like, right? And so that's why we kind of get that grayish tones here. And so that can kind of be the manifestation of this higher refractive index material as well.